Now let's consider this problem here. So we have a mass up here. The spring is unstretched at 60 degrees. Theta equals 60 degrees. That means what? So we have 2 meters length of the legs. So it's going to be 1/2 times the length. So it's going to be 1 foot, or excuse me, 1 meter. So the unstretched length is actually 2 meters. Let's see. Here's the spring constant. (1.5 megagrams), 1,500 kilograms. Okay. And let me turn off the laser pointer unless I really want it. There we go. Laser pointer off. Potential energy of the load, mgy. Y is going to be this 4 meters times the sine of theta. So here's 4 meters sine of theta. Here's the 1,500 kilograms times the acceleration due to gravity, and h is some constant. Okay, that's the gravitational potential energy. So yeah, you don't. Here's what the book says. H is a constant. When you take the derivatives, it's not going to matter. Elongation of the spring. So based on theta, that is 4 meters cosine theta. There it is, right there. Minus 4 meters cosine 60 degrees, because you're told when theta equals 60 that the spring is unstretched. So it's the difference between the two. And keep going. So elastic potential energy, K is, where's K again? Where did it say what K is? 18 kilonewtons, 18,000 newtons per meter. 1/2, 18,000 newtons per meter. 4 cosine theta minus 2 meters. There it is. The stretching of the spring squared. So simplifying the math, this is what you get. Next slide. Adding the two, taking the result from the previous results, we get this. And remember, h is a constant. So when we take the derivative, it's not going to make a difference. So here we have 18,000 for, anyway, that's the derivative of this stuff here. Set it equal to 0, you find out where the equilibrium is, and you can use an expression like this. Trial and error, that's another way of saying use the solver in Excel or the F0 function in MATLAB. 45.1 degrees. Second derivative, you get this. Substitute what you just found, the 45.51, into this equation and see if it's greater than or less than 0. So One solution is less than 0. Another solution is greater than 0. So this is the stable equilibrium at 45.51 degrees. Okay, here's an interesting problem. We have a block mass M resting on a cylinder, and it's unstable if H is greater than 2R, so we want this value here to be less than 2R to be stable. Potential function. The elastic, there's no elastic potential, no spring potential at all. It's just gravitational potential. Now, let's take a look at what happened. So, and I disagree with the book. This theta should be r sine theta, right? So it's this distance right here, which is r sine theta. It's not r theta. It won't matter to the analysis, by the way. So y equals this, the total height equals this, and from which you get the potential energy. And when you differentiate, instead of an r sine theta, you get an r theta. And you set that equal to 0. For small angles, by the way, theta approximates r sine theta. Now, how is this? Y equals r sine theta. So here's r, here's r sine theta, and I would think it would be r sine theta squared. So I think this is a mistake in the book. Crunching the math, you get this, you set it equal to 0, sine theta, when theta equals 0, that satisfies it. When theta is greater than 90 degrees, in other words, the darn thing is hanging upside down, it also satisfies it. So you can figure things out. Second derivative of the potential energy, you get this expression. And like I said before, theta here is approximately equal to the sine of theta at near 0 degrees. They're approximates of each other. So the final result here, whether or not it's stable, is the previous mistaking sine theta for theta is not a problem. It's unstable. This is negative if H is too big. And if H is small enough, it'll rock back to its equilibrium position. That is kind of a interesting result, that when you displace it, you'd think that gravitational potential energy increases, so it would just keep going. But the trouble is, it rolls down that cylinder also. So if by changing its angle, its change in center of mass is less than the change in height due to the cylinder, then it will just rock back to the top, which is very interesting. I think I need to 3D print this and show it. So with that, that is the end of the